Hello, everybody. I'm Javier Cano from Intercon. We are a Spanish manufacturer for refrigeration systems. We are not a big multinational like the ones that we have had before, but we have very interesting presentation to show you. Well, I'm going to talk about the low-charge ammonia technology. I will start with an initial thinking. The technological development in refrigeration system has mainly been has followed mainly several strategies. One of them is energy efficiency. Another one is natural refrigerants. Obviously, all this is driven by the main driver is the fight against climate change. But in the following years, there is another very important driver we have to look after, and is the scarcity of resources, not only energy, but also material resources. The strategy to have compact systems with very little use of materials, it will become more and more important. Also, low charge is part of this reducing in the use of natural resources. So that's why my presentation is that important. Well, these are the content. At Intercon, for the past 15 years, we are a young company. We are, this year is our 15th anniversary. We've very much focused on reducing the charge of the refrigeration system along our small history. And if we look to the very early or traditional historical ammonia systems, pumped ammonia system, overfeed ammonia system, that they used over 4 kilograms of ammonia per cooling kilowatt. Now we've reached. Our last developments are the critical charge ammonia chillers, which they are using 50 times less ammonia than the conventional systems. In the middle, we have many other systems with HFCs, like a compact system, large monoblock industrial systems, also HFC chillers with 1348, for instance. But in the end, we reach the ammonia chillers, the low-charge ammonia chillers that they, as you will see later, they use just 70 grams of ammonia per cooling kilowatt. This is very important because this is the lowest charge you will ever find in the exhibition. You may find another chiller with a little bit, with a slightly smaller charge, but that's a water-to-water chiller. I'm talking about the air-to-water chiller. Well, what is then a low-charge system? There are many criteria. If we look to the regulations you have on the right, there are different regulations across the world. The US, in the States, for instance, they call low charge to low overfeed systems, for instance. And they have a regulation on health and safety, and everything that is below, for instance, below 500 pounds for them there's no hazard declaration. That could be low charge for them. In the European Union, there is no harmonized standard. Some countries like France, they have also a threshold, which is 150 kilograms. Below that, they consider that there's no hazard declaration needed for the ammonia installation. If we look, for instance, for the EN 378, which is not health and safety, but it is rather a design regulation for refrigeration systems. They also have some requirements depending on the refrigerant charge, but as I said, this is not for the installations, that's for the refrigeration circuit, for the refrigeration system. So there are another important regulation like the EDR for the road transport. Below 50 kilograms, they consider that there's no hazard at all, so you can use a standard transport by road. So if we look to the duration, if we really get to stay below the 50 kilograms of ammonia, that is very convenient because we can manufacture packaged chillers already pre-charged in the factory that can be transported by road. So let's say that 50 is a very good value. If we have a look to the other criteria, let's say the different systems, the technological, let's say, criteria, we see that in the different countries, for instance, in the States, they consider low charge what they call the low overfit systems, and that would have a specific charge of around 1.5 kilogram per cooling kilowatt. In Australia, for instance, they call low charge what they call direct expansion system, centralized direct expansion system, and they are around 1 kilogram per cooling kilowatt. In Europe, we are rather talking about secondary systems. And in that case, as I said, we can be as low as 0.07 kilogram per cooling kilowatt. Well, in the middle, we also have the distributed direct expansion system I also will talk about, which is around 3 grams or 0.3 kilograms per cooling kilowatt. I'll talk about this, the low charge technology in distributed direct expansion systems. This is typical P&A of a direct expansion system. This is quite new, actually, because we started with a system like this 1 year ago, and we have very good results. The technology behind is what you can see here. We use the microchannel condenser. It's a dry condensing, which is also very interesting against the evaporative condensers. We use these semi-hermetic compressors with a screw compressor with a permanent magnet motor, direct expansion evaporator. This is a tube and fin coil, which is a key to the low charge technology. Then we use the direct cooling of oil. And well, the oil is very important here because we use a miscible oil. I will talk about it later. And also, well, here in this case, we use heat reclaim for hot glycol for the frost. This is let's say a one-to-one system, or in this case, there are two evaporators. We have to use hot glycol for defrost. We cannot use hot gas. In this case, as I mentioned, we are in a very low charge as well. I mentioned we are around 300 grams per cooling kilowatt. And if we look to the chiller, the technology behind is very similar. There's some few differences. In this case, we have a plate evaporator. It's a full stainless steel plate evaporator, which has a very low charge of refrigerant. We also have the expansion valve and also the miscible oil state separator. And there's one important thing here is there's no liquid receiver, because in dry expansion we have a small liquid receiver. In the previous technology, here we have no liquid receiver at all, so it is what we call a critical load chiller. And as I said, this is the lowest specific charge you will find in the exhibition. So the key issues behind the direct expansion ammonia systems. We have the direct expansion evaporators. The refrigerant distribution is very important because this is dry expansions. We need enhanced exchange surfaces in the tubes in case of a tube and fin coil. These enhanced these are microfin tubes inside, and these are very likely to get oil falling. So then the oil is also key here, and actually the miscible oil will help to wash out the oil from the surface. I'll talk about that later. The compressor is also important because as we have very low charge, we cannot allow any leakage at all. So we need to have a semi-hermetic compressor. In this case, it's gas-cooled semi-hermetic compressor. So also if ever there is any small liquid return, the compressor it will always re-evaporate that. We have, as it is a gas-cooled motor, it's important to have also a high-efficiency motor, a permanent magnet rotor. Also, the liquid cooling, we do that with economizer. And one important thing in when doing dry expansion of ammonia is to have a look to the water content in ammonia, because it can it will create a glide, an important glide in the end of the evaporation. So we cannot really allow any water in the circuit. And there are several ways of eliminating water in the expansion systems, like distillation, but in our case, is thanks to the oil as well. So as you know, the oil in a refrigeration system will always migrate to the evaporator, even if you have a very good separation. With the miscible oil, we ensure that the oil will be returning to the compressor. So we don't really need with one stage separator is enough, because any oil leaving the compressor will finally also return through the suction line. We know that we have no need for purging or a purging system or special maintenance. Will work on its own. In this case, we use an air cooler for the oil to keep the right temperature. This also, compared to a thermosiphon system, it will result in a lower refrigerant charge. And as I said, the solubility the mixability of the oil with ammonia is, in this case, is in the whole range of operation. There is a very good thing about the oil is we use a PAG oil that will trap any moisture in the ammonia, and it will return it into the polymer chain, so it keeps the ammonia dry. So this is the construction, how it looks like. We use this type of condenser, V-shaped condensers, that will characterize both the ammonia chiller or the ammonia condensing unit. It's like a modular construction. One of the V actually is the oil cooler. The air cooling is very important in our technology. I mentioned that we use microchannel condenser with a very low charge of ammonia, but compared to the evaporative cooling, it gives some advantages. Historically, the evaporative cooling has been used in ammonia forever. There is very little use of air coolers. But and there's some reason for that. That's some historical reason. There were some assumptions on energy efficiency, which are true. They say that evaporative cooling can be more efficient than air cooling, but normally it ignores the cost of the water and the consumption of the water. And there is a recent paper from the International Institute for Refrigeration that is comparing both systems, and they conclude that taking into account the cost of all the utilities, both energy and water, they get up to 30% of savings with the air coolers. This is an example of an ammollite chiller in a meat processing industry in Spain. This is a more than 700 kilowatts, and it has 2 times 35 kilograms. Let's say 2 circuits with 25 kilograms each. This is another example. This is 2 condensing units for blast freezers with a direct expansion of ammonia with a very low charge. Each blast freezer has 50 kilograms of ammonia. The capacity is 125 kilowatts at minus 35 degrees. This is what it looks like. The condensing units on top of the blast freezer, and then we have the evaporator inside, and we call it turbo freezer because we have 3 big turbines are pushing the air through the load. This is at 25 tons of meat, which processes in 24 hours. Everything is monitored with a monitoring system for control. The process takes 24 hours to cool down, to freeze the meat. And the customer recently told me that they had got, the cost of energy per processed kilogram meat was 0.1 kilowatt hour per kilogram of meat, and that was a third of the what of what they had in a HFC blast freezer. And finally, we've performed a life cycle course for this system applied to a cold room, as an example, comparing it with HFC system with transcritical CO2, with a cascade propane CO2, subcritical CO2 system, and then the low charge ammonia system. We can see how the life cycle cost of the ammonia system, despite the higher initial capital expenditure, finally, the life cycle cost is lower thanks to the lower operating expenditure. So, this is the end of my presentation. Low charge ammonia technology is an eco-friendly solution. It's safe and reliable thanks to the low charge. Very easy to install. It's plug and play, really plug and play. Fully monitored with the latest digital technology. And as I said, has a quick payback compared to a cheaper conventional system. Thank you very much.